guys. We get started here. So my name is Mathew Gardner. I am a developer. I've been working with Elixir for a couple of years now. It's been fun. It's my favorite language. I'm going to show you some other languages. Don't stone me. You know, it's going to be fine. There's going to be Python. There's going to be C, but mostly Elixir. I think that's going to be the most fun. And that was what I was supposed to say at that slide. So actually, though, let me just say, I work at Toyota Connected. I've been there for about 1.5 years now. And I started learning machine learning things on my own on the side just because it's interesting. It's a lot of fun, but it's a new thing for me. So as I was doing that, I actually stumbled on an opportunity at Toyota Connected to start learning machine learning with machine learning guys, the guys that are actually data scientists and are actually creating these models, and I'm able to work on a project with them. And so I started thinking about some of the problems that we're doing, and they want to do everything in Python, and I want to do everything in Elixir, and I just want to see how can we put the two together? Where can we bring that machine learning model closer to the Elixir ecosystem? So I did a big research project to try and see what we can do. Whoa, I'm learning this new slideshow too. So what is machine learning? For the guys, have you all done any machine learning? Like, have you learned taken any online classes and anything like that? Or a little bit here, like it's interesting, right? It's fun? Cool. So I might just skip over some of this then. So just real quick, it's computer science meets statistics. What we want to do is get a program to we don't want to have to tell the program what to do in order to be better. So we want it to learn from the data that it's seen, and use the data as past experiences from which to learn. What is a model? It represents something that we've learned from our data set. So that might be a matrix with whose values are learned weights. That might be used for some math, or it might be the slope of a line. You can think of it as a black box function. We have some data, and we have some features, and we're going to pass it to this function called predict, and we want to see an outcome from that. But maybe we don't know, as developers, we may not even know how that works, because there are many different models, different ways you can model things too. And at the end of the day, we have an API that we're using that we give it some inputs and we expect some outputs, and it's just a function. So here's an example of linear regression, and you can see that it's just trying to find the line that fits best to the data set that we have. Here's an example of a classification where we have some samples and we can kind of draw a line somewhere, and because the data sample is on one side or the other, we can say it is this class or that class. So for my example here, I'm using the iris data set just to keep it simple. We have, in scikit-learn, we have this data set that we can just load, and we can use its features and its targets for its labeled data to train a model very quickly and easily. So we have 150 samples in this data set. It has 4 features. It has the sepal length, the sepal width, the petal length, and the petal width. And some guys have gone and measured all of these values and have labeled them. And so we know that these values are these classes, this species of iris. And so what we want to do is take this model that we've trained, and when we get new data that we haven't seen before, we want to see if it can accurately classify the species of the iris. So here's one. This is the setosa. Here's another, the versicolor, and the virginica. So our goal is to identify species of iris from the set of measurements that we have. So these measurements are the features. There's 4 features. And this is a supervised learning algorithm because we have labeled data. And so we want to train this model to we want a statistical model to be able to use and make predictions with. So here's what our data looks like. This is a random set of 150 that we have. So here's just some 5. And you can see we have our features are in centimeters, and then we have some classes. We only have 3. We have 3 species. We have 0, 1, and 2. Those other species I showed, these here. Sorry. So another way we can look at it is by plotting it. This is a plot that only looks at the sepal. We have the length and the width. And just by looking at it, you can tell we could probably put a line right up there between red and the others and accurately predict the right species for that data set, for what features we may get. Another way to look at it is you can see that they kind of cluster. In this space over here, there's this species with these measurements, and this space over here, another species. So let's get into the code. So I chose to use a support vector machine for this because we want to do classification, and we're going to use the linear SVC class in the scikit-learn library. So what we're going to do is we're going to import our modules, and we're going to load the iris data set. And to follow convention, I like to use X and Y. X is a matrix of our features, of our training data, and Y is a vector. They call it here data and target, but everywhere else you'll see X and Y. We're going to create a classifier, and then we're going to fit it to the data. And that's going to train. And all of the scikit-learn classes follow the same API. It's this easy to use all kinds of different models. You could actually take the same data, swap out the linear SVC for a random forest, and it's the same API. And you just see which one works better. You just try it over and over and over again. So it's a big experiment. But we'll skip over that and just generate it once, and we'll save this file. Or what we'll do is we'll pickle what we have generated. And that's a Python way of saving something so we can retrieve it later. So now that we've got a model, what do we do? How do I use that in production? So what we'll do is we could have a microservice that loads this model, and we can interact with it over HTTP. That's kind of what we do a lot. But you might find that in the machine learning community, there's a lot of GRPC. If you're going to use TensorFlow, which I'm not going to talk about neural net stuff today, but if you were using TensorFlow and you want to use TensorFlow serving, you can generate a GRPC service with that model, and you don't even, I mean, that's the way they're going, so you should know about GRPC. Ports, I think this is really cool because inside of Erlang or Elixir, we can call a Python function from inside there and inside our app and treat it just like it was an Elixir function. And then NIFs. So a NIF is a native function that we can take and load into our app. And then finally, Elixir. We'll see where we go with that. So I might just gloss over some of this stuff because we all know how to do HTTP. But this is what it looks like in Python, just a simple HTTP server. We're going to load our stuff. We're going to load the model, and we're going to keep it in memory, and then we're going to define our post handler. We're going to unpack the payload, parse some JSON. We're going to take this list of feature. So we have a matrix, an M by N matrix, and that is, M is the number of predictions we want to make in this Go. N is the number of features that we have. So once we unpack that, we can pass that to the predict function on the model that we're grabbing off of the server context that we'll place there on server start. And then we get a predictions back, and we're going to send back, OK. We're going to say 200 OK, here's your list of predictions. Here we make a threaded HTTP server, and we put the model on the server context so that we can access it in the request handler. So in Elixir, it's pretty straightforward. Just use create a function here and create a payload and send it along over to Poison or something, HT Poison. It's just one way to do it, to quote coworker, and get back a prediction. We're making one prediction here. We're not making a list of predictions, because as a client, you're probably only looking to make one prediction right now. The server side can take a batch of them, and that would be more optimal. But on a client side, we're making one prediction. So the same thing in gRPC. There are advantages to using gRPC. So it's HTTP2. It has a long-lived connection, and it has header compression. This connection can be multiplexed. So you will have a channel in your Elixir side, and they call them channels. And you can make many requests and get many responses on that one channel. So you won't have to keep a lot of them, just one, unless you're doing client-side load balancing. So we use protobufs here, and we're going to define our service. It takes a prediction request, a prediction reply, and the prediction request is going to provide a list of features. So each feature is a message of properties, the 4 features, the sepal length, et cetera. And we're going to get a reply back, and that's going to be a repeated list of integers, 0, 1, or 2. Here's our features. We have the sepal length and width and the petal length and width. We will use a command line tool to generate code from the protobuf. And we won't look at that code because it's really uninteresting. But now we need to make our GRPC server. So it's just like HTTP. We're going to load the model, and then we're going to start the server. And we're going to place, can't really see all of the stuff. I was worried about this. But we're going to place our predict function in there, and we're going to pass it the model, so that when it's initted, it'll have the model so that the request handler can actually use the model. And then here we are. We're receiving the model on a init, and we'll save it. We define a function to do just like we did with our post handler. We're going to unpack the features. We're going to pass them on to the predict function, which is a scikit-learn model function. And then we will return our prediction reply. And this might help. Oh, it was already over. I'm sorry. So I got a different view than you. Oh, no. OK, well, let's move on to ports, because that's what's more interesting. So I'm using ElixirPort. It's really cool, because you can call Python functions, or even Ruby if you want, from Erlang, which is pretty neat. You can do the reverse, and you can pass messages back and forth. It's using standard in and standard out under the hood. It's doing a lot of stuff for you. I think it's worth it to look into. So now you might see that our Python code's getting smaller. We don't need a Python server anymore, so we just need a function. So we're going to load the model, and we're going to define a function that's really a wrapper function to call the scikit-learn models function, the predict function, and then turn it into a list so that ElixirPort can understand it. Yep. So in Elixir, we'll just create a gen server, and we'll start it up, and we will use :Python. This is the module you get with ElixirPort to create a PID that represents, it abstracts all that stuff for you. I don't know if I can scroll over, but what we do is we tell it which which Python interpreter. So we have Python 3.6. The next tuple in the list there you can't see is really just the Python path. And right now it's just // It's the root of my project. And we'll save that PID as our state in our gen server. We'll create a function, like a public API function here, that will accept 4 args. These are the features. And then we will handle that call with those 4 features and say Python call. And we're going to say, we're going to use this port. This is already open. And we're going to want it to call iris.py, which is the Python I just showed you a minute ago. And we're going to call the predict function. It's basically MFA. It's module function arguments. And you can't see it here, but there's a list of args there. the 4 features. And then we're going to reply from our gen server the prediction that you were looking for. And then we're going to be good, and on terminate, we're going to stop. If you don't do this, you can create a whole lot of Python processes that might not get cleaned up. I actually went into Observer, and I had this gen server supervised, and I just killed it to see what would happen. And I was seeing just a bunch of Python processes stay, because every time the gen server came up, it would just pile up. And so you're going to have some system overhead if you let that happen. You don't want to do that. So now NIFs. This is the scary stuff. You probably don't want to do this unless you know what you're doing, or if you know C, or if you're a masochist. If your code crashes, it's going to bring down the beam, so be very careful. And if your code is going to do a lot of number crunching, like in machine learning, you might need to be responsible and try to yield back to the VM so that you're not tying up all the time. Also, these functions are public, so anybody could call these. So you have the extra responsibility of treating the arguments that come in and appropriately returning something back or rejecting to do something, because if your C stuff crashes, then the beam's crashed. So, to quote Spider-Man. And this happened to me earlier. This is a screenshot of a GitHub repo. You can't see it. It's public, I promise, it's there. But it is a library called SKlearnPorter. And what it can do is take your model that you made and generate code for you in another language, which is pretty cool. So it supports C, JavaScript, Ruby, Python, PHP for some reason. And a lot of the classifiers will export to this. I didn't really see any regressors there. So I generated some C code from our support vector machine. And this is what it created. So you'll note that it generated some hard-coded numbers, these are the learned values. And this is what's most important. This is what we're interested in. And this predict function. And it's just a nested for loop. That's the implementation of predicting the class with a support vector machine here. It'll also generate this main function that we don't care about, so you can just throw that away. I mean, you could keep it if you want a CLI tool, and you can call predict from the command line, but we won't need it for our NIF. So we'll start writing our NIF code here. We need to include earlnif.h, and we're going to write a wrapper function. It's going to accept an environment from you have to pass around, but that you'll get when it's called from Elixir, and you'll get argc and argv, etc. So now we need to define some C terms for our features, and we need to get the Earl terms into C terms. So that's what we're going to do here, using earlnif's library to turn these into doubles. And we're going to make an array of these features because our generated code is expecting this. And then we just call predict, passing that array. We get back a C int, and then we're going to return back an Erlang int. And then we're going to export this function. And what this is saying is we have a function named predict with arity 4 that we're going to call this C function called make prediction, which was my wrapper. And we're going to say it's dirty. We're not going to be safe about it. So to make it, we need to make sure that we get the Erlang path, because the earlnif stuff is in there, and we need to add it to our compile flags. You can see -i Erlang path. And then we're going to compile the shared object. So we're going to compile the generated code, the iris.c, and the nif.c that I wrote. You can barely see the full command. And then we have a module in Elixir that on load will load the NIF in the priv folder called nif.so. And we're going to define a function that if for some reason it's not loaded, we can blow up. And we'll make a mix task so that we can have it make, so that every time we run, we can make sure that it does compile. But we need to add that to our list of compilers in mix.exs. So, Elixir. I took that library and I saw how it worked, and all it did was it had a text file with handlebars in it. And it was just some C code with handlebars, and it just injected those learned values. So I was like, well, why not Elixir? So I forked it, and I made it generate Elixir. So I thought it'd be fun. I didn't think it'd be practical. I thought, this is stupid. I shouldn't do this. But let's see what it does. And I was surprised at what I found. It's really fast. That makes sense. It's compiled. But I thought it would be high memory, and I haven't quite profiled that yet. So I'm still suspicious. But it was pretty fast for this particular model. Almost as fast, man, I'm not even sure anymore. It was as fast or faster than the C, and that doesn't make sense. So I'm still testing that. It's still a work in progress. But Elixir and even the NIF, they're eligible for hot code reloading, and that's interesting because you might have a pipeline of you got new data and you're training new data or training new models. And if they're more accurate or whatever, maybe you need to report you're calling some Python script that's generating a new model, and if it's more accurate, then export it to Elixir or C or whatever. And there you go, new model in production. So here's the Elixir code I came up with. This is probably not the best way to do. I tried to just copy and paste the C code and convert it functionally. Here's these learned values that we saw in the C code. And this is the outer for loop. I had to do a zip and a reduce. And in the inner for loop, I had to do another zip and a reduce. And then we had an if statement in the outer for loop, and this is just a condition. At the end of this reduce, we return the last known class. And so at the end of this execution, we have the predicted class. And I've tested this with all the methods of all the HTTP, the Python predict, and this predict, and the C predict, and they all get the same result. So I know it's correct. I don't know if it's the best. There is room for improvements. What I've showed you was just a basic gen server. We want to utilize CPU cores and keep the memory low, but also keep request latency low. What we can do is spawn workers. That will allow us to spread over our CPU cores. We want to maybe keep a resource pool of ports. If we're going to use ports to call predict, then I noticed that it wasn't really being concurrent. Because at the end of the day, it's still a process. It still has a mailbox, and it's doing one thing at a time, is what it looks like to me anyway, in my empirical observations. So you can create a pool of 2, 3, or 4, maybe as many as CPU cores as you have. I don't know if that makes sense. I think you'll have to tune it and see where you go. Your mileage may vary. Or you could batch them. So the client side wants one prediction, but we can use OTP to batch them up, and we can create a buffer. So our gen server could become, just take that same gen server, and when we call predict, it just adds to its state into the list. And until a threshold or maybe a timer to flush it out, it could then go and pass all of those features that we want to predict for all at once. And the SKlearnPorter predict function, it will actually slice up that array and run over all the cores it has access to. So that's not a bad idea. So this is a work in progress. I'm still trying to profile it and also try it with different algorithms. I started with the support vector machine, and I've done a little bit with the random forest. The random forest was a little, I thought trying to write Elixir code for it would have just been a little nasty, just because a random forest is an ensemble of decision trees, and decision tree is just a bunch of if-elses. And it would have been a really long code. When you trained a model, you would have had, a huge depth, and I didn't want to go in. I thought I wouldn't be able to show you the code if I had to scroll 2,000 lines. So you may need to tune in production because every model will be different. And we don't know, even when we found a model that we really like, we're not sure how it's going to behave. So what your strategy is depends on what you're trying to do and at what scale. But so far, I really like ElixirPort because I want to use the right tool for the job. I like Elixir, and I think we can make our platforms with it, and we can use it as a glue language, and maybe it's a way to escape the Python global interpreter lock to drive a lot of our stuff. But there's still a lot of libraries in Python that are better at just handling math and big matrix stuff. So we could pass that all on to Python and let it do it, get the outcome, and save that. And that's it. Does anybody have any questions?
Yeah, so my question is when you're using ElixirPort. So when you're using ElixirPort to call the Python, it's loading a file for the weights or whatever it ends up being. And so does it have to load the weights every time you call it, or is there a way to say, load the weights and then it just lives in memory, call the function as many times as you want?
From what I gather, the ElixirPort is starting up a Python process, and that is running, and it's apart from the beam, and it stays open. And in the Python script, we loaded the model, and so procedurally it goes and it loads the model. It's in memory.
So it would load it every time you called, because you're calling the whole file, right?
That's a good question.
Because ideally you would, load.
I worked on the assumption that it was staying open, but I think what you're getting at is that, yeah, the Python process is open, but it's still reading the file every time.
Right.
Now, it might be cached as well. I'm not sure. That's a good question to follow up on.
Cool.
Thank you.
That was a great talk. Thanks.
Thank you. Anybody else?
So I have just a very basic machine learning question. So in general, if you don't know very much about machine learning like me, how would you figure out how much is a good amount of machine learning to learn, and how would you go about that?
How to learn about machine learning?
Yeah.
I'm still doing that. I started off just, hey, I'm going to take this Coursera class like that, the Andrew Ng one. Just do that because it's pivotal. And then I started taking some Udacity classes. They're not free, but at least you get some hands-on experience doing some stuff. And then I was very fortunate that I could just do it at work now. So I'm just absorbing what I can from the machine learning guys and the data scientists that we have. So I would just find all the online sources you can get, take those free classes, go to scikit-learn and TensorFlow's docs and just start reading. Just find examples, go on Kaggle, and find people's examples of, they have these kernels or these notebooks, and you can just read through them and see how they did it. I lack the intuition of, we saw this graph. Well, I mean, it was obvious when you could draw a line through, but how did you think of maybe rendering it in 3D space and clustering it? Like, I don't have that, so I'm still learning.
Okay, thank you.
So you mentioned that you were interested in understanding how memory was affected with your models in Elixir. Mm-hmm. Do you have any sense if it would be possible to do the Elixir version of the model in like nerves and sort of the embedded low memory world? I mean, I know there's a lot of ways that you could try to optimize it, but do you think, like, sort of with what you've done, you could get, it would be reasonable?
I think so.
Yeah.
What I noticed, what surprised me was that it was really fast, so fast that, and I, like I said, that's why I'm interested in memory, because it may be fast, but maybe it's ballooning up on the memory, I don't know. But it kind of went against my intuition, so I'm very suspicious of why it was so fast. And it might be some optimization in the beam that it's doing, that's why it's fast. I don't know. I'm still looking into it.
Okay, thank you.
What's you mentioned that you were able to do this at work. What is like the real world use case for the machine learning that you're doing at work, or can you speak to that at all?
I think why I wanted to do this is born out of wanting to get a model, get it in production. We have our platform written in Elixir, and I'm working with a team that doesn't do Elixir. They write everything in Python, and their services are written in Go. But they still do their machine learning stuff in Python. They could probably do Go. That one library generates Go code too. But because we have a strong platform in Elixir, and all of our business logic is there, I wanted to see how much closer I could get to it. Because at the end of the day, I'm calling a black box function. First, you might think black box service, then a black box function, and then we generated some code, and it's a white box function because we could see what it's doing. I thought that was really interesting.
Thanks.
Have you looked at all at TensorFlex or any of the other Elixir machine learning libraries?
For TensorFlow bindings,
Right.
not yet. That's my next step. So, no.
Yeah, so I was just wondering if you could talk about, like, do you think this would work for like unsupervised learning, where you're dealing with more abstract models?
So I really took advantage of that library y'all couldn't see. It generated code for me to easily get it to Elixir, right? And it mostly only supports classification. So I started off wanting to do a regression, and I found that was going to be harder than I thought, or at least in the time that I had, right? Because we could just implement that straight up in Elixir if you know how to do the math and do matrix stuff, but not enough time.
Anyone else? Thank you.
Thank you.